All right, there we go. All right, so the last time we had formal lecture was on Friday. On Monday, we had lecture quiz number 2. So I will try and return the grades for lecture quiz number 2 within the week, or sorry, within 1 week of the test. So by next Monday at the latest. It's the next test on my list of tests that I have to mark. Every class had a midterm or term test this week, so it's sort of just a process of trying to get through them. The next lecture quiz is, and I should also mention like where we are here. So this is March 2nd, 21. The next lecture quiz is scheduled for March 22nd, I think it is. Let me just check that really quick. Yeah, March 22nd, which would actually be 2 weeks from next Monday. So I might move that quiz, like push it back another week or so just to give us a little bit more spacing in between them. But we'll just kind of see where we are by the 15th and how much material we've covered. And then I'll make a decision about how that quiz is, if that quiz is going to be on the 22nd or a week after, so we can study a little more material before having the quiz, just so that it isn't too short of a content quiz. But as I said, I'll let you know once we get to the 15th, I'll make a decision about that, and I'll let you know if we're going to have it the next week or 2 weeks. So the 22nd or the 29th. Okay, in terms of the material, we also have an assignment due. So assignment 3 is due March 12th, 21. So that's not this Friday, but the Friday after March 3rd. Oh, thanks, Parveen. So that's not this Friday, but it is the Friday after, or a week from this Friday. And that assignment has a question on ratio regression, and I believe it also has a question on comparing the variances from ratio and regression estimation to simple random sampling estimation. So we have seen an example of how ratio estimation works if we are interested in estimating the population ratio. So just to go over this idea briefly, we're going to see another example of this, this type of calculation momentarily. The work that we are doing right now, so if we go back to slide number 9 here, slide 9 summarizes effectively the estimators that we are working with in the context of this particular problem. So the starting point again is we have a population quantity of interest. We want to estimate this population quantity. In these examples, we are collecting simple random samples. So we have talked about 3 different sampling strategies to date. We have simple random sampling, systematic sampling, and stratified sampling. Right now, we are focused on the simple random sampling strategy and extending the type of information or the type of estimator that we can utilize from a simple random sample. So in these particular illustrations, what we have done is we have essentially collected a bivariate simple random sample. And what I mean is we have collected an SRS. Let's say that there's 50 observations in this particular SRS. We have for each observation a measurement on the variable of interest to us, which is what we call mu y. So the mu y here would be the variable of interest. And then we also have some auxiliary variable that we call x. So we're able to compute an estimate for the mean of y and an estimate for the mean of x. We're able to compute an estimate for the standard deviation of the mean of y and an estimate for the standard deviation of the mean of x. What we are also able to do is utilize these individual estimates at the same time to construct an estimate of what is called a ratio. And the ratio is effectively just, as you can see here, a fraction where you have the variable of interest in the numerator and the auxiliary variable in the denominator. So if we want to estimate the variable of interest, if we want to estimate the population ratio, we take our estimate for the mean of the variable of interest, we take our estimate for the mean of the auxiliary variable, and we divide one by the other. And then we can bound that estimate using, for example, a 95% confidence interval, where the standard error for our ratio estimator is given here on slide number 9. So this is a pretty classical problem in the context of the kind of examples that we have been working through in the class. Again, we have a sampling scheme, we have information from the sampling scheme, and we're using that information to build an estimate for the population quantity of interest, which in this particular case, again, is this population ratio of the variable of interest to the auxiliary variable. Okay, so in the first illustration, we were interested in predicting the population ratio of the amount of harvest on a particular farm over the area of that farm. Okay, so here is our scatter plot that shows the relationship between the harvested amount of crop and the area of the particular farm. We had 50 farms in this particular simple random sample. So again, we can think of this as 50 bivariate measures. So each observation is contributing 2 variables, the amount harvested and the area of the farm. Now you'll notice here that we have a straight line relationship between the 2 variables. This is an important aspect of ratio estimation because we assume that the auxiliary variable is useful to us when we have an actual relationship between it and the variable of interest. And we describe that relationship in the traditional sense. So we describe it in the terms of linearity. So the correlation between the variable of interest and the auxiliary variable is going to be strongest when they have when the 2 variables have a strong linear relationship. So we're focused on linear correlation in that sense. Okay, so the process of estimation follows directly from slide number 9. So we have estimates for the mean of Y, we have estimates for the mean of X, which are the amount harvested and the area. We can build an estimate of the ratio of the amount harvested to the area simply by dividing those 2 means, and that gives us 154.62 bushels per acre. Then we can bound that estimate using the formula given, or using the traditional formula, or the formula for the variance of the population ratio estimator, square root multiplied by the constant. In this particular example, we don't need to use the FPC because we have the FPC being, or the fraction 1 minus 50 over 1,000 being equal to 0.95. Okay, so that gives us the result that's shown on slide 11. So all of this, again, should be familiar to you. We've been doing these kinds of examples throughout the material we've studied in the course. So from lecture 2 onward, effectively. Lecture set 2 onward, effectively. Okay, and in this particular case, again, the difference is that we are estimating the population ratio. So the quantity of interest is a unique quantity of interest compared to the types of quantities we are typically interested in building estimates for. That being said, it is a function of the 2 means. So those are traditional estimates in the sense of what we have looked at so far. Okay, so to start today, the new material for today, we're going to look at another example of estimating a population ratio. So this is going to be the same example, or the same type of example that we had just reviewed, just in a different context. So what we have here, sorry about that. Okay, so what we have here, are estimates, or we have a population of 67 Ethiopian coffee beans. Pretty good coffee bean, makes pretty good coffee. In the table below, we have some information from the simple random sample that was collected from this population. So we have the cherry index and the sweetness index for each of the different coffee beans, okay? We have 30 measurements in our simple random sample. We have the mean of the cherry index and the mean of the sweetness index, and then we have the standard deviations of each index as well. Okay, so we want to build an estimate for the population ratio of the sweetness index to the cherry index for illustrative purposes. Now, in order to validate this ratio estimate, we need to check to see if there is evidence of a relationship between the two quantities. Okay, so here is a scatter plot that shows the sweetness index modeled against the cherry index. Now, I think that we can all agree that this scatter plot shows that there is certainly a linear relationship between sweetness index and cherry index. Okay. I'll just write between X and Y. Okay. So this implies that we have some, well, it should also show that this shows a positive linear relationship. So hence positive. Okay, so the scatter plot is showing that there is a linear relationship. To determine the exact strength of the linear relationship would be difficult using only a visualization, but we can say that it's a positive linear relationship because as X increases, Y also increases. Now, as is true in any situation where you're working with linear correlation, the sign of the correlation value is of interest to us, but negative correlation doesn't mean poor correlation. So what we would want to see is a linear relationship in either direction, so increasing or decreasing. Both of them would be acceptable and both of them could be strong relationships. But what we would not want to see is any sort of cloud-like shape. So we don't want to see the points essentially randomly scattered across the scatter plot because that would indicate lack of relationship, and that would mean that the ratio estimation procedure is or the value of the auxiliary variable is probably minimal. So again, in this particular case, we have a positive linear relationship that indicates positive correlation, certainly a correlation value that's going to be much greater than 0, but it's not going to be, a perfect correlation because you can see there is some spread between the observations and the fitted line. Okay, so given that we have that relationship intact, we can go ahead and compute our ratio estimate. We can go ahead and compute our estimate for the population ratio. Okay, so we're going to have here theta hat is equal to mu hat over mu hat y over mu hat x. Okay, this is going to be equal to, from the previous slide, 40, what do we have here? 41.44 divided by 41.32. Okay, and that gives us a value of 1.002904. Okay, which implies, of course, that the slope of this particular line is actually very close to 1. It implies it, but we would actually have to verify that through proper calculation. But effectively, what this is telling us is that we have a 1-to-1 relationship between the increase in the cherry index and the increase in the sweetness index. Okay, so now we can bound this estimate. So we have the estimate of the variance of theta tilde is equal to, we'll have to check this thing here. Okay, so okay, and then that is going to be equal to something that's certainly less than 0.95. It's probably going to be closer to 0. Somewhere in the range of 0.5 to 0.65 would be my guess. Let's check this real quick though, so that we have the actual value. Okay, so then here we're going to have 1 over mu hat x squared multiplied by 1 over little n over capital N multiplied by sigma hat r divided by little n. Just make sure that's what I called it on the previous slide. Yes. Okay. There's a lot of symbols in this class. Okay, so now our variance is going to be 1 over 41.32 squared multiplied by 1 subtract 30 over 67 multiplied by 12.26216 divided by 30. And then that gives us 0.000173. So you can see we have a very small variance here. So that would imply that this is well, a very precise estimator, well, approximately a very precise estimator in this case, because again, the estimate for the population ratio is approximately unbiased. And then we have beta is, or the bound is equal to 1.96 multiplied by the square root of the estimate of the variance of theta tilde, which is going to be 0.02648. Okay, and then we can just quickly finish it off, though I think everyone will be comfortable with the last part here. So then we can say the 95% CI is going to be between 1.002904 plus and minus our bound and that gives us 0.976 to 1.029. All right. Okay, so that line that was superimposed on the scatter plot that we used to evaluate the relationship, that was actually not the least squares regression line that we would typically use to superimpose a line onto a scatter plot. That line was actually just a line that passes through the origin and the point mu hat x, mu hat y. Okay, so that is, it is the line with y-intercept equal to 0 and slope equal to theta in this case. So our 95% confidence interval gave us evidence that the sweetness index increases by roughly 1 unit with every unit increase in the cherry index. Okay, so the estimate that we calculated is telling us the rate of change of the variable y with respect to the variable x. So in that sense, it is interpreted and treated on that scatter plot just like the slope of a traditional regression line. Okay, so we have seen ratio estimation now when we're interested in estimating the population ratio. So we've effectively seen ratio estimation in let's say like the most simple context, direct estimation of the population quantity of interest. Now what we're going to talk about are more traditional estimation approaches based off of the ratio estimate. So what I mean by that is we're going to return to the problem of estimating a population mean or a population total or a population proportion, which were the estimates that we were focused on beforehand in the simple random sampling, systematic sampling, and stratified random sampling units of the course. Okay, so the benefit of ratio estimation in the context of estimating a population quantity like the mean. First off, what ratio estimation is allowing us to do if we are interested in estimating, say, the mean of a particular population, is it is allowing us to include the information from the auxiliary variable. So the point here is effectively to make a more informed or to build a more informed estimate. Now, again, in order for this auxiliary variable to be useful to us when we are interested in estimating, say, the mean of y, we require that auxiliary variable to be correlated with y, which would mean that they share information. So this idea of correlation means that there's a relationship between the two, and the change in one is related to the change in the other. So you can imagine that if you have an auxiliary variable that is uncorrelated with the variable of interest, there's no reason to include that auxiliary variable in the estimation scheme because it's not contributing any information. But on the other hand, if it is correlated with the variable of interest, it could be beneficial to include it in the calculation of, say, an estimate for mu, because that additional information could be beneficial to us in the sense that it could reduce the variance around the estimate of interest. Okay, so again, a concept that we have talked about and studied slightly, but not in a lot of depth yet, is this idea of comparing at different styles of estimates for the same quantity. Now, what I was trying to explain there, just to go over it in a different way, is if I want to estimate the population mean of variable y, I could use a simple random sample estimator for the variable of y directly. That estimator should be better than the ratio estimator or equivalent to the ratio estimator if there's an auxiliary variable that's uncorrelated with the variable of interest, which is y. But if the variable of interest is correlated with this auxiliary variable, the inclusion of the auxiliary variable in the estimation scheme could reduce the variance of the estimator, which would make it a better estimator or estimate based off of the criteria of minimum variance. Now, how strongly correlated the variables actually have to be in order for the inclusion of the auxiliary variable to be valid is something that we will talk about a bit later in the lecture set. But for now, you can imagine that we know that zero correlation is of no benefit. We know perfect correlation means you want to include it with direct certainty. But what is the cutoff, right? So how strongly correlated do the variables actually have to be for that auxiliary variable to contribute useful information? It's a difficult question to answer, and you can imagine that the other estimates that are a part of the system are going to help us answer that question. So what I mean is that the strength of the correlation would depend on sample size and variation. So we would also have to be able to estimate those and use them to determine how strong the relationship has to be. Okay, so it's really the same setup as it was before. So we're still working within the simple random sampling context. So for each observation in our SRS, we can measure the value of X. We assume that we have complete knowledge of X for the population, so we know mu X, and we assume that there's a relationship between Y and X. And again, we would like this to be like a strong linear relationship. Okay, so we assume the relationship between the two populations can be described using the linear model shown here. I'll call this 1 for this slide. So we are writing that we assume that the value of Y in the population of interest is equal to some ratio theta times the value of X in that population of interest plus some noise. Okay, so the noise term could be 0. If the noise term was 0, we would have a perfect linear relationship or a correlation of 1 or -1, depending on the direction. But more than likely, you're never going to observe a perfect relationship. So that noise term is going to be some value different from 1. And it can vary from observation to observation. It can be consistent across the whole system. This is the same idea as with linear regression and the idea of the residual term. Okay, so if the average noise is roughly 0, then the relationship between the population averages can be written as follows. So we have mu hat or mu for Y is equal to theta times mu for X, which is equal to mu for Y over mu X times mu X, which is equal to mu Y. Okay, so you can see how the use of the ratio estimate multiplied by the mean of the population of the auxiliary variable leads to an estimate, a value for the mean of Y. Okay, so we are going to utilize in our ratio estimation scheme the estimate of the ratio that we had defined beforehand. So we are going to define mu hat ratio here. This is going to be the estimate for the mean of Y, which is mu Y, using ratio estimation. Okay, so mu hat Y would be estimate from SRS. Mu hat ratio is estimate from SRS using ratio estimation. So the point here is simply to clarify that mu hat Y and mu hat ratio are estimates for the exact same quantity, but they are being computed in different ways. So mu hat Y is the traditional estimate of the mean from a population where you have a sample with one variable attached to it. So it's the sum of the values across the sample divided by n. Mu hat ratio estimates the same quantity, but it takes the mean of population of the auxiliary variable and multiplies by the estimated ratio. Okay, so these two values again are estimating the same thing, but they're being computed in different ways. In particular, the ratio estimate is utilizing information from the auxiliary variable. Okay, so we can derive the properties of these estimators. This is a fairly simple derivation because each of these quantities follows directly from the properties that we established for the ratio estimator. Okay, so for example, the expected value of mu tilde ratio is equal to the expected value of theta tilde times mu X. This is equal to mu X times the expected value of theta tilde, which is equal to mu X times mu Y over mu X, which is equal to mu Y. Right. And this is really just re-emphasizing the same point that we had before. I should probably note that this is approximate given the derivation we had for the ratio estimator. Okay, so these are approximately unbiased. If the ratio estimator is unbiased, then the estimate for the mean based off the ratio estimator will also be unbiased. But what we can clearly see from this derivation is that the expected value of mu from the ratio estimate is the same as the mean of y. So the same as the estimate for the mean of the variable of interest. So the same conclusion as in the traditional SRS case. Okay. The variance for mu ratio is going to be the variance of mu x multiplied by theta tilde. I guess I should write that in the same order. Okay, so you can see what's going to happen here. We're going to get cancellation in the mu x, right? So this is going to take the mu x out front, multiplied by the variance of theta tilde. We already derived the variance of theta tilde, which was 1 over mu x squared times the FPC times that variance of the ratio over little n. So we're going to get cancellation here, and then we actually end up with a much simpler estimate, which is of that form. So the mu x is canceled out in the variance, which is nice. Okay, then we can show that the standard error of mu tilde ratio is equal to the square root of 1 minus little n over capital N multiplied by sigma hat r over little n, which means that the 95% CI for the mean of the variable of interest will be found in the normal way. Well, will be found in the normal way where we have multiplied by 1 minus little n over capital N sigma hat squared r over. Okay, so let's look at an application of the ratio estimator for the mean. So in this example, we have researchers are interested in estimating average brain size among 300 psychology students at a university. It's kind of interesting, actually. So measuring brain size is an expensive process, as you could imagine, and it requires the use of an MRI. So we know that, or the researchers in this case know that brain size is actually correlated with body weight. And body weight is very cheap to measure. So if the 300 students in this particular program are treated as the population, we are able to measure the body weight of all 300 students, which means that we would know what mu x is equal to. Okay. Now, the reason why that is important is because, again, our ratio estimator requires that we have the population mean of the auxiliary variable. Now what we can do is collect a smaller, let's say an SRS from those 300 students. And then we can utilize the SRS to build an estimate of the ratio. And then we can find an estimate for the mean brain size based off of that ratio. Okay, so a sample of 38 students was collected using the SRS. Okay. And the figures below show the brain size and weight for each subject in the study. Okay, so the gray points in the back that you see here, these are the relationship between the brain size and the weight of all of the students in the study. Now, For the purposes of the illustration, we're actually assuming that we don't know this, but the reason that I have the scatter plot shown here is so that you can see how the relationship between the sample acts with respect to the relationship between the full population. So this plot here, so the gray values here, this is for population. Okay. Now the black parts here, okay. So the black dots here show the sampled values. So we can see that from the original population, our simple random sample of 38 students compared to the 300 students, I think it looks pretty good. It's sort of interesting to see that we kind of caught some of the like outlying points here, right? So if we look at these 4 points, these are, these 4 points here. So those are sort of on the higher brain size, lower weight portion of the population. So those would be the students that don't really follow the pattern as much as you would expect. Now you can see that in the middle of the population, so where the bulk of the observations lie. So you can see that we have a lot of students that weigh between about 160 pounds and 190 pounds, and they have brain sizes between about 90,000 and 100,000 pixels or so. That majority, we have some values being pulled from there, but we're missing quite, we didn't quite sample as many as you would imagine from sort of that center point. But, you recollect, if you're able to do this multiple times, you'll probably have some samples where you pull more from that middle, which would be expected given that the bulk of the observations kind of lie in that area. But nonetheless, what we can see is the sample values themselves do appear to show us that there is a linear trend, or at least that there is a positive trend. So if we sketch kind of a straight line through the middle of this here, right, we can say that, or we can see that those black points, they're certainly pretty spread out, I think. This could be a scaling issue, but well, I shouldn't say that. It wouldn't be a scaling issue, but you can see that the points are, they're fairly spread out. So there's quite a bit of variance around the straight line that I have sketched on the plot, but they're certainly showing that there is an increasing trend. So it is showing that as weight goes up, we are seeing an increase in brain size as well. So we have evidence in that sense of this linear trend being intact. All right. Okay, so here we have, we can assume so the scatter plot shows there is a positive relationship, positive linear relationship between brain size and body weight. Okay, so we can use the ratio estimator to estimate mu y. All right, so we're going to have, in this case, mu tilde ratio. So the ratio estimates this is going to be 906,754.2 pixels divided by 151.5 pounds multiplied by mu x, which is 172.5 pounds. So actually we can see that the sample underestimated the true mean of the population by about 20 pounds, almost 21 pounds, right? So it kind of shows too that that sample that we collected was much more on the lower edge of the weight variation, which is, I mean, this is something that can happen when you collect a sample, but obviously you'd like to see them being a little closer together. Okay, and then this is going to give us an estimate of 1,035,176 pixels per pound. No, wait, pixels. Okay. All right, and then if we want to construct a 95% CI for this, okay, so we can write the PC check is going to be 1 minus 38 over 300, which is equal to okay, so then we're going to have that the standard error of mu tilde ratio is equal to the square root of 1 minus 38 over 300 multiplied by, so this value should be given to you. So this is 120,948.9 divided by 38. Okay, so I'll just write here, given sigma r squared 9. Okay, so this is going to give us a value of it's actually very small, 52.72289. So then our 95% CI for mu y should be in the area of 1,035,073. Yeah, rounded to a whole number to 1,035,279. No, that wouldn't be correct. Actually, that might be okay. Just make sure here. Yeah, that's okay. Okay. Wanted to make a little note here, but kind of ran out of space. So I'll just kind of describe it. So you can see that so here, so note that mu ratio adjusts mu tilde y upward since mu x is greater than mu tilde x. Okay, so the note here just says, notice that mu tilde ratio adjusts mu tilde y in the positive direction since mu x is so much greater than mu hat x. Okay. So I mentioned before that you can see that there's that discrepancy between the true value, the true mean weight of the population of 300 students and the estimated weight based off of the SRS that we collected. Now, as a result of that discrepancy, you can see that mu ratio is pushing mu tilde y upward a bit because that ratio is greater than 1. Okay, so does anyone have any questions? Sorry, I didn't really pause at any moment so far. Sorry, are you done? Like 2 minutes. Okay, so I'll wrap it up there for today then. And on Friday, we will pick up with ratio estimation for the total, and then we'll continue to work through lecture set 4. So if you have any questions, let me know. Assignment 3 is due next Friday. And again, I'll try and have quiz 2 back by Monday.